All right, so notes for today. Looking at definite integrals, Riemann sums, and we're going to connect the dots here. But before we connect the dots, let's remind ourselves about the individual dots before we start connecting. Definite integral is the actual area under the curve. So the integral from a to b of f of x dx, even though we don't really know how to evaluate that yet, that represents that area. We can approximate that, estimate that, with rectangles or trapezoids. And we can do left rectangles or right rectangles or midpoint rectangles. We could do all of the above. We could shove more rectangles in there to make it more accurate. But whatever we do, it's an approximation. So now we can start answering these questions. What's the purpose of Riemann sums? Approximate the area or estimate the area.
Under the curve, right?
Under the curve. So we will approximate the area under the curve with rectangles. Well, maybe they're left rectangles. That's what I'm drawing there. I think we've mentioned this. How can we get a better approximation using Riemann sums?
More rectangles.
More rectangles. If we use n rectangles in a right Riemann sum, what is an expression for each little delta x? Okay, so let's put in some rectangles on this picture over here. Right now it doesn't really matter how many you get, so just kind of equally space them, and however many you get. That doesn't really matter. Besides, we want to eventually shove more and more in there. So each width is delta x. Each of those widths is delta x.
But how do we get that?
Well, if there's n rectangles and this full width is b minus a, so the full width is b minus a. I got n rectangles in there,
Divided by n?
so b minus a over n is the width of each rectangle. And again, as n goes up, that's what we want to happen, then delta x gets smaller. That makes sense. You shove more rectangles in there, they get narrower. All right, what is the expression for the height of each rectangle? And we said we were going to do a right Riemann sum. So our first rectangle has a height, so f of, well, it's not f of a because it's moved over a little bit.
F of a plus delta x?
It's f of a plus delta x. Yeah, let's go with that. The next rectangle has a height, so a y value, f of, well, this point right here.
It's 2 delta x?
Yep, we're at a, but we moved over 2 spots, a plus 2 delta x. The next rectangle f of a plus 3 delta x.
Huzzah.
Dot, dot, dot. You get the idea. We don't need to do all of them.
No dots and etc.
So in general, the height is f of a plus some multiple of delta x. So I delta x.
I thought I was imaginary.
Not in this case. Yes, sometimes I is imaginary, but for this, I is a counter from 1 to n. So in the first rectangle, I is 1. Second rectangle, I is 2. Third rectangle, I is 3, and so on.
I kind of looks like a running person. But that's something wrong.
And then that last rectangle is the nth rectangle. Right, the area of one rectangle is, I'll start with just basic geometry here, height times base. I think, I usually say base times height, but it'll look nicer if we say height times base. So we already have the height, that's this, f of a plus I delta x. That's the height. The base, that's delta x. And so if we add up all of the rectangles, here's that symbol that some of you don't like, the sum from I equals 1 to n. So sum up everything counting from 1 to n. And the sum we want to take is all of those areas. So we're summing up all of the rectangles. So this means add the red one and the blue one and the orange one and the green one and the yellow one and the purple one and the pink one. All the way till you get to the end. Add them all up.
Ad nauseam.
Yes. Now here comes the fun part. If I really want to get an accurate number or an accurate area, we could let the number of rectangles go to infinity. That's where things get a little funny, because it's like, well, I can't actually add up an infinite number of rectangles. Like, I don't have the time to do that, because it would take forever. But calculus can deal with limits. So let's take the limit as n goes to infinity. And everything else is the same. We're still adding up all the rectangles. We just now happen to have an infinite number of rectangles. Add up all the rectangles. But now all the rectangles is like literally all of the rectangles. A lot of rectangles. By the way, when your calculator does an approximation of this, when you can put this in the calculator, obviously it doesn't go to infinity. I don't know how many it picks, but when it evaluates an integral, what it does is adds up the rectangles. And I don't know how it picks, how many rectangles it uses, but that's all it does is a bunch of base times height, base times height, base times height, base times height.
Set.
And on fancier calculators, you could set it to say, give me at least 20, give me at least 100, whatever.
But 1 every 1.
Yeah. Okay, so the definite integral is not an approximation anymore. It's the actual, that's the actual area under the curve now. It's no longer an estimate. That is the area if we could somehow do an infinite number of rectangles, which would be kind of wild. Okay, well, this next step is another sort of weird one. We're going to take all of that, and Leibniz said, you know what? I don't like writing all that. Let's instead, we could write it, this is what he called the antiderivative, all of that. And that S, it's an elongated S. So there's the evolution of S's. Sum, sigma, that's the Greek S. S for sum, stretch it out, and that's where you get your integral sign.
And then you just put f of a plus I delta x.
So we have all of this, but we might want to remember that delta x is equal to b minus a over n. All right, you got to know that. Good news is a lot of it is matching, and so you don't have to memorize everything. Once you figure out how to match it, then you can use the matching on the rest of the worksheet. Kira, is that what you did? So she worked ahead. You don't have to know everything to do the matching, and then once you have the matching done, you can kind of use that to help you with the rest of it. But we don't have matching first. Let's see if we can try these on our own. Number 1, write the integral from 3 to 7 as the limit of a Riemann sum. Alright, well, I know it's a limit as n goes to infinity. Sum all my rectangles from I equals 1 to n. So that's going to be the same on all of them. Let's see. A picture isn't absolutely necessary, but maybe it's helpful. I don't know what f of x looks like. Oh, I guess I do, but I don't care about the x squared plus 1. I'm more thinking about 3 to 7. Okay, so let's think. I'm summing up all the rectangles, so I want to do height times base. So the height would be f of 3 plus I delta x times delta x. That's not my final answer, but that's a pretty good start.
Why'd you write that if you were going to divide I of x by something?
Because I was mixing up things in my head. I know that delta x is b minus a over n, so I was thinking about dividing, but I don't divide yet. I'll divide when I put delta x in. So limit n goes to infinity from 1 to n. Okay, f of 3 plus I delta x. So I'm going to plug in 3 plus I delta x right there. 3 plus I. I'm also going to replace I delta x with b minus a over n, which I can actually do b minus a. That's 4. Squared plus 1. So I'm squaring the x and then adding 1. And then that's the height. The base is b minus a over n, 4 over n. Let's do one more before we start to talk about patterns. Limit n goes to infinity, sum from 1 to n. Let's see, 8 to 2, kind of going backwards here. Do I need to rewrite this step, or can I skip to plugging it in? I'm going to plug it in, so it's going to be sine of x, which is, let's see, what's our starting value is 8. 8. But I'm going backwards to 2.
Minus delta x?
So minus I, and then delta x. What's delta x for this one? Negative 6 over n. So be careful because we're going backwards. So minus I 6 over n.
Well, no, wouldn't it be? Oh, never mind.
Yeah, because I put the negative there.
Never mind.
Plus x, which is 8 plus, 8 minus 6i over n. There's my height times my width, negative 6 over n. Why don't you try number 3? Try number 3. I'm going to press pause. Try number 3. Number 4. Try number 4. This one?
Yeah.
Yes, that's also b minus a.
Okay, thank you.
Yes. For C? So for a 2 out in front of there, we can pass on B. A 2 way out in front just means you can just stick the 2 out in front of everybody. limit as n goes to infinity, sum from I equals 1 to n, natural log of 3 plus 2 times, let's see, x is starting at 0, our delta is 1, counter is I. So there's my base, and my height is 1 over n. Now, here's where some algebra can come in. We're going to take this 2, and it doesn't distribute because this is all multiplying, so I can't distribute it to this and this. I've got to pick one. I think it'd be a whole lot easier just to stick it on that one. And let's clean up some of this stuff in here.
But would it be wrong to leave it like that?
No, it would not be wrong to leave it like that, but I want to simplify to show something. So natural log 3 plus, okay, 0 plus 1 over, I can clean that up to just be 2 over n I, and then 2 over n. It's like, well, why would you do that? Except that compare A and C, and they're the same. So you have to be aware of algebra tricks where if they ask you for this and they put this as the answer, well, no, that would be fine. If they ask you for this and put that as the answer, can you recognize, the algebra that went in there? This is the calculus is easy, algebra is hard part of the lesson.
Maybe you could stamp that in part 3.
Number 5. To get a little easier because this is multiple choice, which of the following definite integrals match this? So it looks like we're starting at -5. That's our A value. And we're going to go 6 away. So A minus B is equal to 6.
Wouldn't it be B minus A? Or?
You're right, B minus A. I wasn't even thinking which way. I was just thinking 6 away from -5 means I'm going to start at -5 and go to 1. Tangent. So I like answer choice 1, but the others might be right as well. That's the trick. And I think the only way to do it is to write out 2 in that format and see if they match. So that would be the integral or the sum from k equals 1 to infinity, tangent of -5 plus 0 plus 6 over ni times 6 over n. That's number 2. Is that the same as that?
Yes.
Yeah, the 0 in there would go away. I used I instead of k, but that doesn't matter. That's just our counter. Everything else matches up. So it turns out that's the same thing. That works just as well. And in the interest of time, I'll say that 3 works also, so we don't have to worry about it.
Is it because there's no 6?
And it has to do with that 6 in there. That 6 would distribute to the end. You'd end up with 6 over n, and it'd all be the same. So you have to be careful on those. You think, well, there's no way they're all the same thing, but they are. Let's see. Number 6. For what value of k does this thing equal this thing? Well, let's look at the pieces here. It looks like we're starting at 6 and going 8 away.
So that's 14, yeah.
So that's 14. 6 and going 8 away. So I think K's got to be 6.
Could you do it backwards, like to decode all of that?
Yeah, you could. Yeah. I don't know how else you'd do it. Other than the A number is what starts it, so that one wasn't as hard as it looked. All right, number 7 is going the other way. So integral. What are we starting at? What's our starting number? Have you seen enough of these to know yet? 5. That's our A value. And how far away are we going to go? So if we go 2 away from 5, we end at 7. And then what we're doing with that thing is cubing it plus 3 timesing it. So kind of going backwards.
You could get the original function from that, because it's an antiderivative.
Right, and you could back up one step more. But we will leave it at that.
What is number 9 doing?
So let's skip number 8 and go to number 9. A region is bounded by the graph of y equals 4 minus 3x squared. Something like that. X equals 0, y equals 0, and x equals 2. Oh, so it's trying to tell me that how to set up. So I want to go 0 to 2, f of x dx. Of 4 minus 3x squared. So 4, that doesn't look right. 4 minus 3, this looks good. This one still looks good. I don't like the 4 out front. Which one do you think between A and B? A looks like it's starting at 1. But that's not right.
It's not starting at 1.
It needs to start at 0, which is a little weird because there's not a 0 there. But I think my answer choice is B. Yeah. Alright, so kind of tricky, but the homework you'll see is a lot of matching. And so the first part, if you get all those matched up, things will go a lot better for you. Also remember the AP Classroom quiz is out there, due by midnight tonight. 6 multiple choice questions for 5 bonus points.
Due by 11:45.
Due by 11:45. Yes.
Don't leave people astray, Mr. Wolf.
And I don't think I announced that yesterday, so I'll probably bump that back a little bit.
I thought it was due yesterday by 11:45 when I did it at 5.